Hello and welcome. So broadly, the AppFeld lab uses a genetically encoded sensor to measure redox potential in the C. elegans feeding mussels. We knew intuitively that our sensor could measure some redox potentials more accurately than others, but we didn't have any quantification of that difference. So we built a framework to predict the accuracy of any two-state sensor, and you can use our framework to compare different sensors to quantify accuracy gains made from improved image analysis and more. So now, some background. When I say a two-state sensor, I mean a fluorescent protein, usually a modified GFP, that changes conformation and fluorescent properties in response to some input. So for example, here is the excitation emission spectra of the redox-sensitive GFP we use. In oxidizing environments, these two cysteines in the fluorophore form a disulfide bridge leading to the red spectra, and then in reducing environments, that disulfide breaks and leads to the blue curve. So with these types of sensors, you make a ratiometric dual excitation or dual emission measurement, which we call R. For many experiments, you can just report R, but you can also go further and convert that into a biochemical value, like redox potential in millivolts or pH or molar ligand concentration. And that's often useful for the same reason why it's useful to convert the amount of mercury in a thermometer to a standard unit like Celsius. But in all of these sorts of sensors, this map is very nonlinear. It's always some hill function. And our problem is that we often don't consider the error propagation from R to that value. So for example, in the redox sensor literature, authors often assume that sensors are good at measuring near their midpoint potential, or the pH equivalent is their pKa. But that's not always true. Here's a plot of observed versus expected redox potentials for our sensor. And the black line is what would happen in a perfect world with infinite accuracy. In other cases, the error explodes as you get further from some center point. But the center point isn't the midpoint potential. It can be far from the midpoint potential and actually depends on multiple sensor properties. But luckily, this graph is all we need. If we have this graph for our sensor, and we know what error we expect in R, then the error we expect in redox potential is just this graph's residuals, the maximum distance between the black line and a pair of colored dotted lines. So if you make that for a sensor, you can make this plot right here, which shows the redox potential on one axis and the accuracy on the other. Then you can draw some line for how accurate you need to be. And that defines these different probabilistic spaces of redox potentials and accuracies that you can expect to observe 95% of the time. And this graph will be different for every sensor. So if you make this graph for a bunch of sensors and then take slices of this graph at different accuracies, you can compare the sensors, which is what I show here. And this can show you which sensors are better suited to measure certain values and how some sensors might be redundant. So then we took this model and generalized it to any sensor that has two states. And this works for both dual excitation and dual emission sensors. So dual excitation and dual emission. In fact, there's even this one sensor, E squared GFP, that works both in dual excitation and dual emission modes, and it has different ranges of accuracy depending on what mode it's in. So that's kind of cool. And we also use this model to help our own experiments. So first we determined our error in R. You can do this in just one day with GFP, but we looked at tens of thousands of images taken over a 6-year period to show that our error was remarkably consistent. And then we plugged in our sensor parameters along with that accuracy to show how a new image analysis technique could help us explore new, biologically meaningful spaces of redox potential, and also reduce the need for manual curation, which is great. And this method also has other applications, like determining what sensor is best for your experimental needs, or what new sensors might need to be built. And we call this method the SensorOverlord, since it ruthlessly proclaims what you can or cannot measure with your sensor. And I implemented this method as an R package. I also set up a graphical interface that you can access at SensorOverlord.org. So, we really hope this method can help you make better informed decisions about your microscopy. And I really encourage you to check out the links below to our preprint and the public web application. Thank you.